Okay, kids, we're back. Chemical reactions class number 2. We're going to do what's called decomposition reactions. In a decomposition reaction, it's the opposite of synthesis. Synthesis, you build stuff up, small things become bigger. In this case, we're going to have one larger reactant, and it's going to break down into 2 or more smaller products. We always have one reactant. That's an easy way to recognize it. If there's one reactant, it certainly can't bond to anything. There's nothing to bond to. The only thing it can do is to decompose, break into something simpler. Here's an example. We have this compound PbO, lead Roman numeral 2 oxide. It's going to decompose into lead and oxygen. Now, PbO is an ionic compound. Lead Roman numeral 2 means a positive 2 ion. Oxygen's a negative 2 ion. That makes it a 1-to-1 ratio. PbO is going to become Pb and O2. Oxygen, when it decomposes, the individual ions of oxygen are going to end up becoming atoms and bond together in pairs because oxygen is diatomic, a Hunkelbrief twin. And so in order to balance it, in order to get O2, you can't have just one PbO. If you actually have just a single formula unit of PbO, it won't decompose because it'll be too unstable. Every 2 PbOs form 2 lead atoms and 1 molecule of oxygen. A big thing becomes 2, or in this case, 2 small things, 2 or more. Now, in a minute, we're going to demo this hydrogen peroxide decomposition, but for now, let's talk a little more. Decomposition requires a single reactant to break down into 2 or more smaller products. In this abstract is actually the opposite of the synthesis abstract. AB, arrow, that means AB reacts and forms A plus B, A and B separated. So we start out with something and we end up with different things. Now, A and B are just letters. It's not B for boron. It's A and B, the letters. Could have been XY, becomes X plus Y. Now, the word equation for what we're going to do is hydrogen peroxide will decompose into water and oxygen. All right? I know you might say, well, how do you know it doesn't form hydrogen and oxygen? I know that. When it decomposes, it turns into water and oxygen. This is the skeleton here in blue. H2O2 makes H2O and oxygen. Now, I'm going to try to balance this equation right here, right where we are. I'm going to get my pen out so we can do this, and we're going to go real slow. There's 2 hydrogens in the reactant, and there's 2 hydrogens in the product. Now, there's 2 oxygens here. We have 1 plus 2. 2 oxygens in the reactant, and then we have 3 in the product. 1 in the water and 1 O2. Now, in the product side, there's 1 and 2. The odd one is broken. We have to double the odd one and start over. So to balance this, I'm going to put a 2 here. And whenever I do that, I have to go back to the beginning and start all over. So in the reactant, I have 2 hydrogens. But over here now, I actually have 4 hydrogens because I have 2 waters. So that means I have to put a 2 here. Now, whenever I change these big numbers called coefficients, I start all over again, just like Glinda the Good Witch said, always best to start at the beginning. So now I have 4 hydrogens, and I have 4 hydrogens. There's 2 times 2 oxygens. It's O2 twice. That's 4 oxygens altogether. I have 2 oxygens here, and then I have 2 more back here. So now it's actually balanced. 2 hydrogen peroxides makes 2 waters and oxygen gas. Now, I'm going to let you guys watch this now. I'm going to pick this laptop up, and I'm all set up. Let me show you what we got going on here. Let me tip this a little. In my hands, I have this really big graduated cylinder. It's just a giant one. There's nothing fancy about it. It's just bigger than normal. And I have this bottle. It's a gallon jug. Now, I don't know if you can see this. I'll try my best to get it in there. It is 30% hydrogen peroxide. Now, the stuff you have at home is 6%. The only thing fancier with mine, besides it's a white bottle instead of brown, is that it's 5 times more concentrated. And if you get it on your hands, it's not good for you. Lastly, I happen to play a little trick on you. I'm going to tell you about it though. I have some soap for dishes in here, and I literally put 1 drop in the bottom of this just for fun. It's not part of the chemical reaction, but you get to see it later on. So let me show you. I'm going to pour some of this in here. I like to pour a little extra. You know, we're not using up too much stuff this year, and a little extra makes for a good explosion. It's not going to explode. Can you see it? Can you see it? Here it is. It's all the way up here. It looks like we have about, I don't know, 75 mLs. And there's a couple of little bubbles. You see them? That's from the soap when I splashed it in. This is decomposition. Not only is it decomposition, it's going to be really exothermic. It's going to get hot. But if I feel it and you can't feel it, this is actually it's pretty chill. And if you were here, I'd let you touch it. You'd be like, wow, that's not hot. Also, it's not doing anything. It's kind of boring. Now, as it turns out, let me try to get a better spot here. As it turns out, it's a terribly slow reaction. Terribly slow. Is boringly slow. But if we let this go, say until next Tuesday, we're going to have we'll have a big graduated cylinder filled with water, and the oxygen bubbles that come out are going to probably be so few and so small per hour, you won't even notice it. Let's hurry it up. I happen to have what's called a catalyst. A catalyst is a chemical, usually a chemical, that will allow the chemical reaction to go faster. And it doesn't change the reaction, it just lets it go faster. So instead of waiting until next Tuesday, we'll do this in like, I don't know, 20 seconds. All the heat that's going to come out, it's going to come out in 20 seconds. All the oxygen that's going to come out in 20 seconds. So let's put this in, and then we'll talk about it again, okay? So here we go. This is potassium iodide. It looks like table salt. And I'm going to put 1 little chunk in. Here we go. And we'll give it a couple of seconds. Let me do some magic here. See my hands? Come on, come on, come on. And see the bubbles are starting to come out? You see them? Come on, show, put on a show. My kids are waiting here. So here it comes. It's a lot of bubbles. Let me feel. It's still a little cold. We'll see what happens. Come on. Come on, more bubbles. Now, the reason you can see those bubbles is because there's a little bit of soap in there. The soap catches the gas that's coming out. That gas is oxygen. They're coming out the top. They're coming over the top. Holy smokes. Come on. Come on. And it's happening, and it's happening, and the temperature's getting a little bit warmer. Maybe we'll put a little bit more of this potassium iodide in to hurry it up so we don't have to wait so long. Uh-oh. I put a lot in now. Look at it now. Can you see the steam coming out of it over here? Can you see all this smoke? It's not really smoke, it's steam. And I can feel it. It's getting really, really hot. And the steam that's coming out is making, you can't see it. My hand is really moist right now. It was dry, and all this came out. Look at this mess that I made. It's all over the place, and it's still coming out. Now, all that happened just there would have happened if I was patient, or if you were patient. But we didn't want to be patient. We wanted to hurry it up and make it go a little faster. So this is the balanced chemical equation. We'll keep talking about it in a second. It's all balanced, so you can see that. Now, this reaction is so slow that you don't want to watch it. So we needed to add what's called a catalyst. The catalyst I added is called potassium iodide. Now, a catalyst in chemistry It's not a reactant and it's not a product. You put it in and it stays there, but you could also take it out. It doesn't change. It's just like an assistant to help move some things from over here to over there. So things can change. The hydrogen peroxide can decompose into water and oxygen, but it's slow. The catalyst makes it go faster and faster. Now, in a balanced chemical equation, we have to indicate we use the catalyst. The catalyst is written above the arrow. It's not a reactant. We don't put plus potassium iodide, and we don't make potassium iodide a product. We just put it up there on top of the arrow to indicate you added a catalyst. Now, overall, there is some energy at the beginning of this, but there's a lot more energy at the back end as a product. So this was an exothermic reaction. Now, the important thing is here, the tube gets really hot, steam comes out. If you were here, I'd make you touch it. You'd be like, wow, that got really hot. It really does get pretty dang hot. The water boils, it gets so hot. The reason the water boils and the reason steam comes out is because the reaction happened in a very little time. If you had that same amount of heat over a long period of time, it wouldn't be enough to make the water boil. You'd end up with water and oxygen, but you'd end up with very little oxygen and very little water per minute. And you would probably not even notice it. But when it happens really fast, it's kind of like, you ever see those videos of a plant? You see the seed and then like 20 seconds later, it's a plant. Plants don't really grow that fast. If you watch the seed grow, you'd never probably see it. It'd be amazing, but you couldn't even pay attention for 2 weeks. But they do that time-lapse photography. It's the same thing here. This is like time-lapse. The catalyst makes it just happen faster. But there is no difference in the products. There's no difference in the amount of energy released. It's just faster. That was decomposition. Now, with no catalyst, the reaction's still going to happen. It's still going to occur. But with a catalyst, it's just going to occur faster. The catalyst is not a reactant. It's not hydrogen peroxide plus the catalyst. The catalyst is written above the arrow. All right, how cool was that? Now, decomposition. We're going to try to write these. I'm going to try to write them with my crazy pen here, and we're going to try our best to balance these. Magnesium nitride. Now, magnesium, you remember Mg, it makes a +2 ion, and nitrogen makes a -3. Now it says magnesium nitride is going to decompose into magnesium and nitrogen. So we're going to write the formula. Mg3 N2. Now, magnesium nitride is an ionic compound, and I told you that ionic compounds are going to be solids unless they happen to be dissolved in water, and there's no water in this equation. Magnesium nitride arrow. This stuff, one reactant, decomposes. And it's going to decompose. I'm having a hard time writing, but please stay with me. That's an Mg, and it's going to be a metal, so it's a solid. And it's going to make, that's a little plus sign, N2, which is going to be a gas. Now, the phase symbols are important, right? Magnesium nitride is an ionic compound. They tend to be solids unless they're dissolved in water. Magnesium is a metal. It's clearly a solid. We're not doing this on the sun. We're doing it in the room. And nitrogen is a Hunkelbrief twin, and it's a gas. There are 3 magnesiums in the reactant, so I need to put a 3 here. And there's 2 nitrogens in the reactant, and look, I already have 2 nitrogens. That was easy. So let me get rid of my clear old drawings, and look what we got. Bada bing, bada boom. 1 magnesium nitride makes 3 magnesiums and 2 nitrogens. Solid makes a solid and a gas. This is called decomposition. 1 big reactant makes 2 or more smaller products. Next one, magnesium carbonate. Oh, we got to get out table E, right? Magnesium carbonate. Let's see if I can pick a new color so we can really have fun. Magnesium's a +2, right? Mg, I'm having trouble, but this is my scrap. Mg plus 2, and carbonate is CO3. It's a -2. So the formula for this stuff is going to be Mg and then C. Wow, that's a big C. CO3, and it's a solid. And it's going to decompose. And what's it going to decompose into? It says it's going to decompose into carbon dioxide, CO2, which of course is a gas. CO2 is a carbon dioxide gas, and magnesium oxide. Now, you might not know that that's going to form into magnesium oxide, this compound, but I'm telling you it's magnesium oxide. Magnesium oxide's a solid compound, though. It's ionic, and you should know that. So there's one magnesium in the reactant, and there's one magnesium. So far, so good. There's one carbon here. There's one carbon here. So far, so good. I got 3 oxygens here. There's 2 here, and there's 1 here. Hey, this one's already balanced. We don't have to do any work. You know, sometimes you get lucky and it's already balanced. It's in a 1-to-1-to-1 ratio. You know, when you become a doctor, you have to take the Hippocratic Oath. You gotta say the Hippocratic Oath before they actually let you become a doctor. And one of the tenets of the Hippocratic Oath is, above all else, do no harm. You're not allowed to kill your patients. You're not supposed to hurt them. You gotta make them better. Here's a balanced equation. It's already balanced. Don't wreck it. Above all else, do no harm. Iron, Roman numeral 2 oxide, is going to decompose. Now, iron, Roman numeral 2, is going to be Fe. I'm having a hard time with this writing business. You know what I mean? Fe plus 2, and oxide is a -2. So the formula is going to be, of course, FeO. And it's a solid because it's an ionic compound, and it's going to make, it doesn't even say what it's going to make. What could it possibly make? It's going to make iron, and it's going to make oxygen. Iron's going to be a solid, and oxygen. Oxygen is going to be a Hunkelbrief twin, O2, and it's a gas. Now, in order to balance this, we're going to have to do some fancy thinking. There's 1 iron, there's 1 iron. So far, so good. There's 1 oxygen, and there's 2 oxygens. Now, when you have a 1 and a 2, it's the odd one that's broken. You have to fix the odd one. You have to double it. The only way to double it is to put a 2 over here in the front, and then we have to start over to keep Glinda off our back, Glinda the Good Witch. There's 2 irons. That means I got to have 2 irons in the product. Let's check it again. 2 irons, 2 irons. 2, look at this 2. See this 2? That means there's 2 oxygens also. And look, there's 2. Bada bing, bada boom. We did this one as well. Let's get rid of these drawings. We'll move right ahead. 2 FeOs makes 2 Fe's and 1 oxygen gas. It's in a 2-to-2-to-1. The lights went out. Give me a second. Come on. If I sit still for too long, the power goes out. It's to save electricity, but pain in my neck, right? This is balanced in a 2-to-2-to-1 ratio. Now, ammonia gas. Ammonia is a liquid. Usually it's a solution, but if it evaporates out separately as a molecule, NH3 gas. Now, that's a formula you should put in your head. It's important, but it's on table L. It happens to be a weak base. So ammonia gas is going to decompose. Now, what do you think it's going to decompose into? It's going to decompose into nitrogen, which is a Hunkelbrief twin, and hydrogen, which is another Hunkelbrief twin. And both of these are gases. I'm not going to write the G's. I'm having a hard time writing, but they're both gases. So let's see what we got going on. There's 1 nitrogen in the front, and I got 2 here. 1 and 2. The odd one is broken. We got to double it. So I'm going to make this a 2. And now I got 2 nitrogens and 2 nitrogens. So far, so good. But look what I got. I have a triple H doubled. I have 2 NH3s. That's a total of 3 and 3 or 6. I don't know, you can see them all? 6. How do I get 6 over here? Can I make that H6? No, it's not a Hummer truck. You can't have H6, but you can get 3 hydrogens like that. And that's exactly what happens. Look at this. 2 ammonias make 1 nitrogen and 3 hydrogens. 2 to 1 to 3 ratio. Ammonia decomposes into nitrogen and hydrogen. Now, this word equation, ammonia gas decomposes, that's enough. What else could it become? That's the only thing it could become. You don't have to say everything. You don't have to tell me twice. If it decomposes, it's going to be nitrogen and hydrogen. HCl is going to decompose. What could it possibly decompose into? What do you think? It's here. Let me get my pen out here. We'll pick a new color too. We'll go with black this time. It's going to make hydrogen gas, which is the Hunkelbrief twin. And I'm not going to write the G, but it is a G. And it's going to make chlorine gas, which is also a Hunkelbrief twin. And it's a G, but I'm not going to write that either. So I got 1 H in the front. I got 2 H's in the back. That's no good. 1 and 2. Which one's broken? The 1. So let's double it. Start over. So now I got 2 H's all together. And look, 2 H's. That's good. And I have 2 chlorines. Oh, look, 2 chlorines. That was easy to balance too. Clear my drawings. We'll jump ahead. Look at that. 2 HCl's makes 1 H2 and Cl2. 2 to 1 to 1 ratio. Dinitrogen pentoxide. Ooh, dinitrogen pentoxide. Now, this is the biggest formula we've seen in a couple of days, right? Let's see if we can't come up with a nice formula for this. Dinitrogen means N2 pentoxide. Pentoxide means oxygen times 5. And it's a gas. I'll put a little G in here. Oh my gosh, these parentheses are hard to draw. Arrow. Now, what's it going to become? Nitrogen, N2, and it's going to make O2. Now, these are both gases. I'm not going to write the G's this time. They're difficult, but they're both gases. So let's see what we got. 2 nitrogens, 2 nitrogens. So far, so good. I got 5 oxygens. 5. There's only 2 over here. Now, when it's 5 and 2, even's good. 5 is the broken one. What do? We double it. So I'm going to put a 2 here. And now I got to start all over. Glinda says it's always best to start at the beginning. So now I have a total of 4 nitrogens in the front. There's only 2 here. I have to put a 2 here so that I end up with 4 nitrogens. 4 and 4 is balanced. Now, how many oxygens do I have over here? It's 2 times 5. 2 times 5 is 10. 10's a big number. I mean, it's all the money I have. $10 is not a lot. It's good to have 10 fingers or 10 toes, but you don't need them all the time. How do we get 10 oxygens on this side? Can I make it O10? No, oxygen's diatomic. In order to get 10, I got to put a 5 there. This is a 2 to 2 to 5 ratio. 2 to 2 to 5. Let's see if this comes up the way we see it. Bada bing, bada boom. This stuff always works. Every single chemical reaction will balance unless maybe you write the formula wrong. Now, if you wrote the formula wrong, you might get it to balance, but you're not writing anything correctly. Dinitrogen pentoxide looks like this, N2O5. Nitrogen's a Hunkelbrief and oxygen's a Hunkelbrief. This is the only correct answer. Generally, only balanced chemical equations are possible. If it doesn't balance, that's your problem. You did something wrong. If you've written everything correctly and it doesn't balance, it's wrong, it's your fault. And if you don't get it to balance, you probably wrote something wrong. You got to figure that out as well. Okay. Holy smokes, we're at the end of this class. All right. I'm going to ask you to do some homework, all right? By the time you're watching this, it's going to be Monday after Thanksgiving. That means tonight you're going to do homework number 1. It's balancing decomposition and also synthesis reactions. You got to tell me which is which. Is it synthesis? Is it decomposition? And you got to balance like 6 or 7 of them. I'm collecting it on paper. I want it in my hand. Don't copy from your friends. If you have any trouble, you call me on the phone or you watch these 2 slideshows again. This is not hard. It's going to get hard tomorrow. It's going to get even harder the next few days. This is easy. If you're struggling, you're just not paying enough attention, or you need more help, and call me. I will help you. Do not copy from your friends. Thanks for watching. Thanks for coming. Bye-bye. Oh, I can't get out of here. It won't let me out. Now I'm done.